Okay, so before I showed you guys two types of addressing modes. Um, the first that I showed you was absolute addressing, which is where we say, like, I want to load the value at 0x6. And it'll take whatever data is in 0x6, in this case. It's a monkey, and it's going to do whatever it needs to do with it. So, that's absolute addressing. You basically give it an absolute address, it goes to that address, and it tries to do whatever it can with it, according to whatever the instruction may be. The next type that I showed you guys was called register indirect. So what I did over there is I took the value hex 3, I put it into a register, for some reason, that's why. I put it into a register. Give me a second to bring that forward. I put it into a register, and then we went to that address and loaded the data. So we used a register to hold an address temporarily. And you can use that, that'll be used for, it's kind of like a pseudo direct addressing. You load a direct address that you can into a register, and you use that address to load your data. And you can do this at multiple levels of indirection. So you can go to, like, this address might be holding an address. So you load that address, and that address might be holding an address. And you can do that as many times as you want. In C, we call that pointers. So it points to an area of memory. In other words, another level of indirection. And then you just go to that area of memory, and you grab the thing. So it's the equivalent of saying, I've got address 3. Address 3 here, well, in this case, it holds a circle or a sphere, but I could delete that. I could put another address in here and say that this thing, I don't know what happened there. That's why, because I had the plane before. So I had this is going to be a little bit hard to see. Suppose I have 6. In that case, let me delete this thing from behind it. That's in the way. So we've got 6 in here. So it'll load 6 on the next one. And then it'll go to the address at 6. GX. Come on. There we go. It'll go to the address at 6 and then load whatever's there. And in this case, it'll load a monkey. Control D and put it over here. And then GX. And there's our monkey. So that's all it's going to be doing for register indirect. You basically treat a certain thing as a certain area of data as an address. You load that address into a register, and then you go to that that address on the next instruction. So in this case, on the next instruction, it'll go to value 3, and we load that data, and value 6. And then we can go and do another level. We can say this data is also an address. So go to address 6, and then load that data, and there's a monkey. So that's register indirect addressing. So what are the other forms of addressing that we have? Well, the most common is PC relative. So the way PC relative works is on instruction 1, our program counter points here, and then when it's done doing that instruction, it points here, and then it points here when it's done with that one. And suppose that there might be like a branch. PC might jump down to here to skip something, or it might jump back, or it all just depends on however you set up in your code for branching. That's what happens when a PC goes more than just like forward. So suppose that we're here and we want to get whatever the address is at hex 3. Well, we know that we're at address 1 because program counter is equal to the address 1. Now, if we add 2 to the program counter, we'll get address 3, and that'll be this location. And if we add 3 to the program counter, we'll get address 4. If we add 4 to the program counter, we'll get address 5. That is the basis of PC offset addressability. So it's all relative to your program counter, where you are in your current program. So when you're doing this, you might, like, this is where branching comes handy. So suppose that we have our first instruction, and I'm going to go ahead and add one more little thing over here. Let me just copy this, and I'm going to give it a label, and it says start, and then I'll have another label over here that says end, and then inside this instruction, the data is actually going to be halt. So it stops the machine. And let me go ahead and put this here. G, Y. Oh, come on. Go over to here. There we go. So we see our halt instruction. And then this over here is just a label for whatever the value is over here. Let me give it a color to make it prettier. Let's do green. So we've got our halt instruction. We've got our start instruction, which I'm also going to have as green. So program counter is going to first go to start, and it's going to keep going through its instructions. Now suppose I add another instruction here, which is just going to be like some sort of condition. And I can say branch to start if true. So in this case, I will go ahead and do something here that'll set condition codes, set CC condition codes equal true for, I don't know, whatever the condition code we're going to be setting. But bear with me. So PC, we're here. We'll set our, we'll do some instruction that sets our condition codes. Then we'll go to the next instruction. And here, our PC says branch to the start if true. So what is the address of start? Well, it's -2 from our PC. So, well, technically it would be PC plus 1 minus 2. So, what happens here is now the PC is going to branch up to here and go again. And it's just going to keep looping down this thing over and over and over again until, for some reason, this gets set to false. So this might be some instruction that sets a condition like decrements a number from not... I'll just say decrement R1, which this decrementing R1 would be the same thing as writing like R1 minus minus in C. And like this value could be Control D over here. I'm just going to set this thing to like 3 to make it simple. So if branch to start if Z, which this if we were writing in LC3, it'd be BRZ for the instruction and then start. So what that's saying is if the Z condition is true, in other words, if R1 equals to 0, or sorry, let me rephrase this. Not 0, I want positive. If this value is positive, go to start. Otherwise, our instruction here is going to say BR and then NZP for doesn't matter what the thing is, if it's negative, positive, or 0, branch to end. So how will this thing work? So I've got the instruction here, and instead of having this as R1, I'm going to go ahead and write it as the LC3 equivalent. So it'll be add R1, comma R1, comma -1. And this instruction over here, start, is technically actually a label. So it just means whatever is in here is going to be like the first, like when you see start in your assembly code, start means the next instruction is going to be loaded to the first start address, or .org, I mean. So over here, I have my, this will actually be the thing. So I'll just say, for simplicity, yeah, add R1, comma, R1, comma, $3. So that'll set R1 equals to 3. Well, the problem with this is if we go and do this, it's always going to set our start condition here. So no matter what, it'll always be positive because after we decrement, it'll go back to 3. So we need to move our start label to here. So how will this program work? So PC opens up. And let me go ahead and actually, since I'm doing that, I might as well make this the same thing as .org and then x0 for this would be the LC3 equivalent as our label. So PC is here at our first address. We load this value in here. So add R1 3. So we'll put a 3 in here. And then we go to the next instruction. We'll decrement 3. So 3 is now 2. And on this instruction, we'll check to see whether this value is positive, which certain instructions, such as add, set condition codes, since that condition code got sent to, the p bit got set, this is going to branch. So it's going to say, okay, what's our offset to our start? Well, we're going to go back 1, basically. So we'll go up to here, and we'll do this instruction again. In this case, it'll do this instruction. It's going to go to 1. We're going to branch down to here. It's going to say, oh, it's still positive. Go back up to here. Set this to 0. We'll go to this bit. It says, okay, we'd only branched on positive to start. Since that condition is not true, we go to the next instruction. This instruction says, branch if anything occurs to end. Okay, how are we going to branch to end? We know that this is our PC plus 1, our PC plus 2. We'll branch over to here, and then we'll halt the machine. So now we do nothing. PC won't move. And that's the basics of our 3 different addressing modes. We covered absolute addressing, where we would load a specific address directly and then go to that data. So we would say, like, PC now equals hex 6, for instance. So PC now goes here. Or we have the register addressing mode, which will look something like this. So, like, we want PC to go to whatever the value is in our R0, happens to be 4, so it goes here. And then the final mode is PC relative, which is relative to your current program counter, what should your offset be? Should I go positive offset or should I go negative offset to get to whatever instruction I want to run? And that's really all there is to it. Those are the 3 main addressing modes that are available in the LC3. Let me know if you guys have any questions. As always, post comments below, and I will try to get to those as soon as possible.